Hello everyone. Today we're going to solve together a problem whose similar versions have been asked in math olympiads. You can see the question on the screen. We are given x plus 1 over x equals square root of 3, and we are asked to find the value of x to the power of 100 plus 1 over x to the power of 100. Let's start solving right away. Let's move the question to the left side. Now, x plus 1 over x is actually a quadratic equation, right? If we multiply through by x, we get x squared plus 1 over x equals square root of 3. Then let's move the x in the denominator to the right side. After that, we move everything to the left-hand side and set the result equal to 0. Finally, we rewrite it in the form we're more used to. Look, this has now become a quadratic equation. We already know the general solution of such an equation. The quadratic formula is minus b plus or minus square root of b squared minus 4ac all over 2a. This particular equation has no real roots. If you plug in the values of a, b, and c, you find x equals square root of 3 plus or minus I all over 2. We can make this expression a little nicer. Okay, now here comes the interesting part. We're going to write this equation in Euler form. Euler is considered by many mathematicians as one of the greatest in history. In fact, mathematics can almost be divided into before Euler and after Euler. And what did this great mathematician say? Such an expression can be written as cosine theta plus I sine theta, and that is actually e to the power I theta. This is a very, very famous equation. In fact, one special case of it is considered the most beautiful formula in mathematics. If you put pi in place of theta, you get e to the power I pi plus 1 equals 0. I will definitely try to make a separate video about this later and explain it in more detail, don't worry. Now, when we bring our equation into this form, cosine theta equals square root of 3 over 2, and sine theta equals 1 over 2. That gives us theta equals pi over 6. So that means x equals cosine pi over 6 plus I sine pi over 6. And this expression is the same as e to the power I pi over 6. In the problem, we are asked for x to the power 100 plus x to the power negative 100. But we can generalize the expression. Instead of putting numbers in the exponent, we can write n. Now pay attention. The first expression can be expanded like this, and the other one like this. Look, on one side we get plus I sine, and on the other side minus I sine, and they cancel each other. We are left with 2 cosine n pi over 6. Perfect. In the problem, we want x to the power 100 plus x to the power negative 100. So if we put n equals 100, the answer comes out as 2 cosine 100 pi over 6. This can be simplified to cosine 50 pi over 3. Remember, cosine has a period of 2 pi. That means every 2 pi, cosine repeats its values. Here we have a lot of 2 pi turns, many full cycles. So I can rewrite 50 pi over 3 as 16 pi plus 2 pi over 3. And that is simply cosine 2 pi over 3, which equals minus 1/2. And remember, our expression was twice this value, right? So the answer is minus 1. That means x to the power 100 plus 1 over x to the power 100 equals minus 1. Very good. But I hope something caught your attention. Notice here we took x equals square root of 3 over 2 plus I over 2. But actually this is incomplete, right? Because the quadratic solution has a plus-minus sign. We didn't consider the negative case at all. We solved the problem assuming the imaginary part is positive. Maybe with the negative part, the result would be different. Let's quickly check that too. Let's make imaginary part negative. Then the cosine value did not change. It is still square root of 3 over 2. But sine becomes minus 1/2. So that means theta equals minus pi over 6, right? Because cosine is an even function, and sine is an odd function. Cosine of negative x equals cosine of x, but sine of negative x equals minus sine of x. Okay, so let's correct this part too. We now have minus I sine pi over 6, which is the same as e to the power, minus I pi over 6. When the imaginary part was positive, we had x to the power n and x to the power minus n, like this. Now if we write the case where the imaginary part is negative, you can see that they are basically the same expressions, just swapped. So whether the imaginary part is positive or negative, the answer doesn't change. We still get the same result, minus 1. Yes, in a question like this, it's pretty interesting that cosine and sine play such a central role, isn't it? Of course, there might be other ways to solve the problem. If you solved it differently, you can share it in the comments. Let's see if you got the same answer. I hope this was clear. See you in the next lesson.